In this video, we're going to look at the derivation of the shortest distance formulae for linear objects in three-dimensional space. So when I say linear objects, I mean linear two-dimensional objects or planes, linear one-dimensional objects, which are straight lines, and also zero-dimensional objects, which are points. And we're going to look at the distances between these given the formulae. So the ones we're going to look at in particular, we're going to look, just for completion, we're going to go from point to point. So a zero-dimensional object to a zero-dimensional object. You should already know that. That's quite easy. The next one we're going to look at is a point to a line. So a point in 3D space to a linear line, a straight line in 3D space. What's the shortest distance between these two objects? We're going to look at a point to a plane. What's the shortest distance from a point out in 3D space to a plane? And then we're also going to look at two lines in 3D space because they don't have to necessarily intersect or be parallel. There's something called skew lines. So these are the four we're going to look at in this video. I'm going to derive the formulae and give alternative methods, which will give a bit more information but take a little bit longer to execute. So that's what we're going to look at in this video. It's going to be quite a long video, so feel free to skip through to the bits you need. And right at the end, I'm going to summarise everything that we talk about, so you can just refer to that if you need it. Throughout this video, though, we're going to have a few different things that are going to come up quite a lot. So we're going to have known points. So a point P, Q, or A, or B, for example, these are going to be known points throughout the video, as in, when I say known points, the coordinates of all of these are numbers that are given in the question. So we've got P1, P2, and P3. Okay, so because I'm deriving a formula, it's all going to be a very general case, but those are numbers that are given to you. Point Q, we're going to say is Q1, Q2, and Q3. If you see an A anywhere, that's going to be A1, A2, and A3. And then a point B is going to be B1, B2, and B3. In general, if a letter has a subscript in this video, the chances are it's going to be a number that you know. And if it doesn't have a subscript, it'll be something you don't know. That's going to be my general rule if I can try and stick to it. Okay, all right, known lines. Okay, so we're going to see equations of lines come up in the case 2 and case 4. So the equation of a line is R, which is the vector x, y, z, is equal to A, which is going to be the position vector of coordinate A, plus lambda times a direction vector D, which is going to be usually D1, D2, D3. Okay, so that'll be the direction vector D. Again, that's known. A is known. Lambda is a parameter anyway, and x, y, z are variables. So that's the known line. If we need more than one line, then we will have a second line for the two-line case here, case 4, in which case we'll have a different point on the line. I'll have a different parameter, which I'll use the letter mu for, and then I'll call this D2, and then that'll be called D1. In a case when it's called D1 and D2, what I'll do is I'll say the vector D1 is equal to D11, D12, and D13, and the vector D2 for a second different direction vector. We're going to have D21, D22, and D23. Okay, so that's what I'm going to use in this video for known lines. Okay. Unknown points. So these are points that perhaps we want to find the location of them, or perhaps we're just going to use them as a kind of an intermediary step, but we don't know what these points are. I'm going to use capital X and capital Y for these, and I'm going to use Greek letters. So alpha, beta, and gamma will be the x, y, z coordinates of my unknown x, and for y it'll be the next three, which is delta, epsilon, and zeta. Okay, so those are my unknown points. We don't know these coming into the question, whereas we would know these coming into the question. And finally, planes. Again, we're going to know the planes. In fact, there's only one case with a plane, which is point to plane. We usually call a plane pi, capital pi, because that's the Greek letter P, and that's going to be n dot r plus d is equal to 0 as defined in the formula booklet. N is a vector that's given to you. That's the normal vector to the plane, and we would write that as n1, n2, n3. R is your variable vector x, y, z, and then D is just a constant which moves the plane up and down the normal direction. Okay, so that's what we're going to be using throughout this video. We may see the plane written as n1x plus n2y plus n3z plus D equals 0. Obviously that's the same thing, but just bear in mind that they are the same thing and they could be used interchangeably. Okay, so that's what I'm going to be using throughout this video, just for consistency really. Okay, right, so let's get to these. So we've got case 1, case 2, case 3, case 4. Case 1 is point to point, then point to line, then point to plane, and then we'll have a look at 2 lines. Okay, so I'm going to go through these. As I said, I think it's going to be quite a long video, so feel free to skip ahead to the bits that you need if you don't need it all. Okay, right, point to point. Very, very, very straightforward. You should have known this from probably the beginning of year 12, really, if not earlier. We've got a point in 3D space over there, point in 3D space over here. I'm going to prove very quickly that it is just Pythagoras in 3 dimensions. So let's say I've got that situation, and then that's a point there. Something like that, and then we go to the cuboid. Okay, all right. So yeah, I'm looking into a cuboid there, and this is my point P over here, this is my point Q over there. I'm going to try to find that distance there, which I'm calling D. And what I can do is I can find the difference in X. So that's going to be P1 minus Q1 modded, just in case it's a negative. Difference in Y, I'll take that distance there. Difference in Y, which is P2 minus Q2 modded, in case it's negative. And difference in Z, which is going to be P3 minus Q3 modded. Okay, right. This distance here across the bottom using normal Pythagoras. Yeah, using normal Pythagoras. We're going to have that as a right angle there. So we've got difference in X and difference in Y. That's a right angle because it's X, Y, and Z directions. So they are all perpendicular, which is why I just hesitated. So this distance here is just 2-dimensional Pythagoras, which I'll call, let's go with D1 as an intermediate calculation. And then if we apply Pythagoras to this right angle triangle here, which that's vertical and this plane is horizontal, so therefore that's also perpendicular, then we can get D. So we're using 2-dimensional Pythagoras twice. So to get D1, that I can say D1 squared is equal to P1 minus Q1 squared. Mods don't matter anymore because I'm squaring it, plus P2 minus Q2 squared. Okay, and then if I apply Pythagoras to this right angle triangle, then I'll get D squared, which is what I'm ultimately trying to find, is going to be equal to D1 squared plus P3 minus Q3 squared. But D1 squared is this thing. So therefore that's going to be equal to P1 minus Q1 squared plus P2 minus Q2 squared plus P3 minus Q3 squared. So therefore the distance D, which is actually what I'm trying to find, that's my distance formula. Distance between 2 points in 3-dimensional space is Pythagoras applied in 3 dimensions, which is difference in X squared plus the difference in Y squared plus the difference in Z squared, all square rooted. And that's my distance formula. Okay. All right, that was very easy. These are going to get hard from this point onwards. I just included that one for completion, really. All right, case 2. We're going to look at a point to line. So you've got to imagine this is in 3 dimensions. We've got a line in 3-dimensional space which has this equation, and then we've got a point somewhere that's not on the line out in 3-dimensional space, and we want to find this shortest distance. And due to the nature of shortest distances, the little line segment between the point and the line is going to be perpendicular to the line. okay? Because if I can move it this way or move it that way, then this line segment will get a little bit longer in either case. So this is the shortest distance and it's perpendicular. Okay, so how do we calculate D in terms of everything that's known, which is going to be my P values, my A values, and my D values? Okay, so I'm going to derive the formula and then just summarise, essentially. So what I'm going to do is I'm going to say that this little vector here, it doesn't matter how long it is, that is going to be the vector D. Okay, that is the direction vector of the line. That's how it's defined. D is the direction. As you vary lambda, you move up and down the line. Okay, that's what it does. And what I'm going to do is I'm going to take that vector D and I'm going to apply it to this point here. Let's call it there, which is going to be the vector D. There. And then what I'm going to do is I'm going to find the point on the line, which I do know is on the line, which is going to be my point A. That vector there. And I'm going to join that vector up there. And I'm going to add D to there. And I'm going to join that vector up there. So I've got this vector here, which is going to be the vector from A to P, which is can be written as AP with an arrow above it. And that vector there's going to be the same thing. And then I've got vector D there and vector D there. And what that has created is a little parallelogram. Okay, so it's a parallelogram in here. And I'm going to use that parallelogram to help me find the value of D. Okay. And the way I'm going to do that is I'm going to state the area of that parallelogram in two different ways. Okay, so the area of the parallelogram can be written as the modulus of D times D, which is the perpendicular height of my parallelogram. So D is this little length here, and then capital D is this perpendicular height here. So the area of that parallelogram is that times the perpendicular. Okay, that's the first of my two formulae, and that's one you would have met ages ago in your mathematical education. The second one is one that we looked at in our previous video, which is the area of this parallelogram is equal to the cross product of the two edges. So the cross product of the two edges is AP cross D, and we're going to mod that because that is also the area of my parallelogram. If you're unsure of where that's come from, then do check out my previous video, the one before this one, and that one will derive that formula for you. The area of the parallelogram is equal to that cross product. And I've modded it because if you don't mod it, then the cross product of two vectors is a vector. Okay, the mod of that vector is the area. Okay, so I've got two different definitions of the area, and that tells me that the area then is mod D times D, and that's going to equal mod of AP cross D, and then I can divide by mod D, and that's going to give me D. So modulus of AP cross D, all divided by mod D. Okay, and that is the formula for the distance between a point in 3D space and a linear line in 3D space. Okay, so A is known because that's the point on the line that's given in the equation. P is known because that's the point out in 3D space that we're looking for, and D is known because that's the direction of my line. Okay, this formula is not given in an examination, so therefore you're going to need to learn it. You need to learn that formula. It's not given, you need to learn it. Sometimes you might see it written as P minus A cross D over mod D, modded. And also in some other literature, you might come across D divided by mod D as being replaced with D hat, which is the unit vector in the D direction. So you might see something like P minus A cross D hat modded. Okay, that's all of these are the same thing. We don't tend to use this much on the MEI course. Tend to use one of these. But you might see that. Okay, that's it. That's the derivation of the shortest distance formula, and that is the formula that you need to learn. I'm going to give an alternative method to find this distance d. It's slightly longer than just plugging things into a formula. However, it gives you a bit more information, and it's going to give us this point here, which is, I'm going to call the point x. It is the point on the line which is closest to p. Okay. Whereas this formula doesn't do that, it just calculates the value of d. All right. So, how do we do that? Well, back to my situation here. I'm going to define this point here as being x. It's an unknown point currently. So I'm going to call that alpha, beta, gamma. And I know that it lies on L. So because it lies on L, the line, then alpha, which is the x coordinate, is going to equal A1 plus lambda, I'm going to call it lambda 0 D1. Beta equals A2 plus lambda 0 D2, and gamma equals A3 plus lambda 0 D3. So alpha, beta, and gamma are unknown. A1, A2, A3 are known. Lambda 0 is a number now, and it's unknown. And D1, D2, D3 are numbers that are known. So this is currently 3 equations with 4 unknowns. Okay, alpha, beta, gamma, and lambda 0. Okay. Lambda 0 takes us to the specific point. It's the value of lambda that puts us at x. Okay. But it is also true that I've got px.n. px.d, yeah. It's also true that this vector here, dotted with d, is going to be 0 because they're going to be perpendicular. Okay, I'm going to use this fact that we've got a perpendicular point here now. So if I take the vector p to x, which is going to be alpha subtract p1, beta subtract p2, gamma subtract p3, that's the vector from p to x, I know that p to x dotted with the direction of the line must equal 0, and what that equation is telling us is that this line segment is perpendicular to the line. Okay, and that's going to give us another equation in my unknowns to give me a 4th equation. So if I go ahead and calculate that, that dot d is going to be alpha d1 plus beta d2 plus gamma d3 minus p1 d1 minus p2 d2 minus p3 d3, and that's going to equal 0. And this is now a 4th linear equation that contains alpha, beta, and gamma. So what I can do is I can take these 4 equations, 1, 2, 3, and 4, and use the GDC to solve, because of their linear. They're linear equations. Okay, and that's it. That's my alternative method. It's a little bit more thinking involved, but solving this system of equations will give you the value of lambda, which you'll be able to plug into here to take you to x. So alpha, beta, and gamma will then be found using the GDC, and then we can find that distance there because we know then the vector px and d, the distance, is equal to the magnitude of px. And we know that vector now because we know what alpha, beta, and gamma are. We already know that P1, B2, and B3 are. Okay, so that's the alternative method. Yeah, like I said, a little bit more work, but it does give you the numerical values of alpha, beta, and gamma, which is the coordinate of the point on the line, which is closest to P, so not just the distance. Okay. All right, so that was case 2, and that's point to line. We're now going to look at points to plane. So here we have a plane. We've called it capital Pi, and it is defined by this equation, n dot r plus d equals 0. N is your normal vector to the plane, r is your x, y, z vector, d is a number that's given, and 0 is, well, obviously 0. And then we have a point P, which is not on the plane, somewhere out in space, P1, P2, P3, and we're looking for capital D, which is the distance, the shortest distance from the point to the plane. Again, just like in the previous case, this little line segment here, that takes us from P to the plane pi, that will be perpendicular to the pi, no, to the plane, sorry, to pi. Okay, that'll be perpendicular. Because otherwise, if you move it a little bit in any direction, that line segment's going to get longer. Okay, so perpendicular and shortest kind of go hand in hand. Okay, so what I'm going to do is I'm going to take another point on the plane. Doesn't matter where it is, but it is an unknown point. So I'm going to call it alpha, beta, and gamma. And I'm going to take this line here, and we're going to be using that angle in there, which I'm going to call theta. Okay, so I'm going to derive this formula using my point x, which is some point anywhere on the plane. Okay, now px, so that's the vector to get from p to x. If I dot that with n, which is the normal vector to the plane, so there's my little n there, just to illustrate what's going on there. That's my normal vector. That is going to equal the modulus of p, sorry, not pq, px, times by the modulus of n, times the cosine of theta. Okay, just by definition of the dot product. All right. Yeah. Okay. Now, because we are interested in theta being acute, so theta is acute, and that implies that the right-hand side is greater than or equal to 0, and that implies that we need to mod the left-hand side. Okay, so we're going to end up with modulus of px times the modulus of n times the cosine of theta is equal to the modulus of px dot n. Okay. Okay. Looking at this right-angled triangle here, bring that one down to there. We know that's going to be a right-angled triangle because that's going to be perpendicular to that line there, because that's the normal direction and that's on the plane. So that's a right-angled triangle. This distance here is px. Then we know that px modded times the cosine of theta is going to equal d. Okay. So px times the cosine of theta is going to equal d, just by looking at this right-angled triangle and applying SOHCAHTOA. So px cos theta can be replaced with d. So that tells us that mod n times d is going to equal mod of px dot n. And that tells us that d is going to equal the mod of px dot n divided by mod n. Okay, so whilst that is true, it is a true statement, I have introduced x into the problem, which is an unknown point. So I need to tidy that up and get rid of my x. So what I'm going to do is I'm going to say, well, p to x is actually just alpha minus p1. Times m1. Plus beta minus p2 times n2 plus gamma minus p3 times n3. I'm going to mod that just in case the top is negative, and then that's all divided by the magnitude of the normal, mod n. Okay, so p to x is alpha minus p1, beta minus p2, gamma minus p3, dot that with n, so times those by each of those components respectively. That's going to give me alpha, so n1 alpha plus n2 beta plus n3 gamma and then I'm going to have minus n1p1 minus n2p2 minus n3p3, and that's all divided by mod n. Okay, how does that help us? Well, we already know that x lies on the plane, it lies on pi, so therefore it satisfies this equation. And this equation is n1x plus n2y plus n3z. So I've got n1 alpha plus n2 beta plus n3 gamma, but plus d equals 0. So therefore, all of this bit here, that's going to equal negative d. And then because of the mods, all of these negatives, all 4 of them, can just all disappear, and I'm left with my formula. So I'm going to say d, the distance that I'm looking for, the perpendicular distance from this point to this plane, is going to be equal to the modulus of n1p1 plus n2p2 plus n3p3 plus d, all divided by mod n. And that mod on the top is just there, just in case the top comes out as a negative number, because it is just a scalar. And that's it. You might see that written as n dot p plus d divided by mod n. Again, mod the tops. And that, I think, is how it's given in the formula booklet, because this one is actually given. So you don't need to learn it. So it's given in the formula booklet. Well, for MEI it is anyway. Okay, so what we're going to do to find the shortest distance is we essentially plug the point into the equation of the plane. Obviously it won't equal 0 because it's not on the plane. So plug it into the left-hand side and then divide that by mod n, and there you go. That's it. That'll be the distance. Okay. Yeah, but that formula is given, so you have to learn it. What that doesn't do, however, is it doesn't give us this point here, which I'm going to call point y. That's the point on the plane which is closest to p. So I'm going to give an alternative method to this, which does find the value of d, but also finds the coordinates of y, which is the point on the plane which is closest to p. So again, we've got an alternative version to look at. So I'm going to call this here y. That's my point y. And y is going to have coordinates delta, epsilon, and zeta, which we don't know. We know P1, P2, P3, we know N, and we know D. Okay. So what I'm going to do is, just like before, I'm going to create a set of simultaneous equations. And then we would use the GDC to solve them. So the first equation is going to be simply that this point lies on the plane. So equation number 1, N1 delta plus N2 epsilon plus N3 zeta. Oops. I at that point. There you go, zeta. That's plus D is going to equal 0. Okay, so that's one equation which contains 3 unknowns. And then the other thing I'm going to consider is the fact that this here, this distance, this vector y to p, that is going to be parallel to the normal to the plane. So yp is going to be parallel to, so some scalar multiple of, the normal to the plane. And this is actually going to be 3 equations. So from y to p, I'm going to get p1 subtract delta, and that's going to equal k times n1. I know what p1 is, I know what n1 is, I don't know what delta is, I don't know what k is. Repeat that for the other 2 directions, so the y direction and the z direction. Okay, and what I've got there is just like before. In the previous case, I've got 1, 2, 3, 4 linear equations in 4 unknowns, delta, epsilon, zeta, and k, and I can use my GDC to solve them. That GDC then, the output will give me delta, epsilon, and zeta, which is the coordinates of y, so the point on the plane which is closest to p, and will also give us k, and if we calculate then k times n and mod it, that will give us the distance d. So D is going to be equal to the magnitude of K times N. So essentially, how many normal vectors do we need to get from Y to P? Okay, which is K times mod N, which we can do that because K is just a scalar, so we can just pull it out. So yeah, mod of the normal, and then times it by K, which is the other number the calculator will give you. Okay, so that's my my method for that one, and that will give you the coordinates of Y. So that's why that one's more useful, but it is a method rather than a formula. Okay. All right, and on to case 4. 4 of 4, last case. We're going to look at the distance between two lines. So we're going to start with two skew lines. So two skew lines, there's nothing analogous in 2 dimensions to skew lines, because in 2 dimensions, lines are either they either intersect or they're parallel. But in 3 dimensions, you can actually have lines which don't intersect, which aren't parallel, lines that don't intersect that aren't parallel. They're called skew lines. So that's the case we're going to consider here. And we're going to find this little distance. So I've introduced a little line segment again. I've called it D, just as in the previous cases, so the distance between these two lines. And because that's going to be the shortest distance between these two skew lines, then that little line segment between those 2 points is going to have to be perpendicular to both of those lines. We don't know the points on these lines, X and Y. My alternative method in a minute will allow us to find those. The distance formula, which is what I'm going to derive first of all, is one which we are going to use. Okay, so I'm going to derive it first, and then we'll use it. So we've got a little direction vector over here, which I'm going to call D1. A little direction vector here, which I'm going to call D2. And then we have a third vector, which we're going to use, which is going to take us from some point on the line, 1, and take us to some other point on the line, L2. Okay, so that's that vector there, and we're going to call that vector BA. Okay, so that's the vector to get between these 2 points on this line. That's going to be useful. Okay, now what we're going to do is we're going to consider a parallelepiped using these vectors. So if we take this vector here, D1, and this vector here, D2, and then we're going to have this third vector going into the parallel, so going into the page. That's going to go there, something like that. I'm going to call that vector BA. And that's a little parallelepiped, and we're going to use 2 formulae to find the volume of that parallelepiped, which will allow us to state the value of D, essentially, between these two. So the first things first is the area of the front face, just as we did a couple of cases ago. The area of the front face, that is going to be equal to the magnitude of the cross product of D1 and D2. The distance D, that is actually this distance here, D, which is perpendicular to the front face and the back face. So therefore the volume of my parallelepiped is going to be equal to the area of that front section, D1 cross D2 modded, times by this scalar number D, which I don't know and what I'm trying to find. Okay. But again, based on my previous video, the volume of the parallelepiped is actually the scalar triple product of those 3. Now the scalar triple product is written as D1 cross D2 dot BA. And just in case that dot product comes out as negative, then we should mod it because it's a volume, so therefore can't be negative. So we've now got two definitions of the volume of my parallelepiped, and we can equate the two together because they both represent the same thing. So we get mod of D1 cross D2 times my unknown D is equal to the scalar triple product D1 cross D2 dot B to A modded. Therefore, my distance formula is equal to mod D1 cross D2 dotted with BA, all divided by the modulus of D1 cross D2. Okay. That formula is given in the formula booklet, so you don't have to learn that one either. Okay. So you are given that one. And that'll give you the distance. So we know D1, we know D2, because those are the two direction vectors of my lines. We know, or we can work out B to A, because that's just a vector to get from one point on one line to the other point on the other line. Okay. So yeah, we know all of the stuff on the right, so we can calculate D. So if you're looking for the distance, it's just a formula plugging exercise. You don't need to be able to derive the formula. You just take these equations of the two lines, and you dump the necessary values into this formula, and out pops D. Great, happy days. However, what happens if you have a more complicated question and you need to find the coordinates of the 2 points in question? Okay, so the point on L1 and the point on L2, which are then closest to the other line. So what's the coordinates of these? So just like in the previous three cases, we're going to look at this from an alternative point of view to find those coordinates. So I'm going to call this point up here X, which is going to have coordinates alpha, beta, and gamma. That's unknown. And then this is going to have coordinates Y, which is going to be delta, epsilon, and zeta, which again are unknown. So we've got 6 unknowns there, plus D is 7. I'm going to try and find those. Okay, now what do we know about X? Well, we know that X lies on L1. So we know that alpha, beta, gamma, that vector must equal A1, A2, A3 plus lambda, or lambda 0, some specific value of lambda, times D1, D2, sorry, D11, D12, and D13. Okay. So we know that's going to be true. And we can apply the same thing to here with Y must lie on my line L2. So this will be B's and this will be D2s. Okay. Okay. So we are able to calculate the vector from X to Y. And that is going to be equal to Y minus X. So Y was B1 plus mu 0 D21 minus X, which is A1 minus lambda 0 D11. B2 plus mu 0 D22 minus A2 minus lambda 0 D12, and then finally B3 plus mu 0 D23 subtract A3 subtract lambda 0 D13, which I know looks hideous, but just remember the only unknowns here are mu and lambda. All the B's are known, all the D's are known, and all the A's are known. So everything is known except for mu's and lambdas. So each of those is just going to be 3 terms at most, with only lambdas and mu's kicking around as unknowns. Okay, now what do we know about this vector? Well, this is the vector to get from this point on this line to that point on that line. And we know that that little line segment must be perpendicular to both lines. So we know that xy dotted with d1 must be 0, and xy dotted with d2 will also equal 0. And that's going to give us two equations with our two unknowns, which we can then use the GDC to solve. Okay, so that's the idea of that. Okay, so let's run this with the algebra. So if I dot that with d1, I'm going to get b1 plus mu0 d21 minus a1 minus lambda 0 d11 times d11 plus b2 plus mu 0 d22 minus a2 minus lambda 0 d12 times d12. I'm going to get plus b3 plus mu 0 d23 minus a3 minus lambda 0 d13 times d13. Okay, so that is the dot product of that and that, which again looks horrendous, but only because it's general case. If you run that through, you'll end up with something times mu 0 plus something else times lambda 0 equals something. And if you play exactly the same idea with this one, then you'll get another equation which looks the same. Something times mu 0 plus something times lambda 0 equals something. And then you can use the GDC to solve that. It's only two unknowns. Once you get those two unknowns, lambda and mu, then if you plug lambda into here, then you'll get the coordinate of x. And if you plug mu into here, then you'll get the coordinate of y. So that gives you alpha, beta, gamma, delta, epsilon, zeta. Once you've got those numbers, then if you need the distance between them, then you can just calculate the magnitude of that vector. The distance is equal to the magnitude of xy. Okay. Yeah, so we know what x is at this point. We know what y is at this point because we've just calculated the lambda and mu value, which gives us x and y. And then hence we can find the vector x to y and then the magnitude of that. Okay, so that's the idea behind that one. Again, it's not a formula, it's a process. It's a bit more long-winded than the formula because it's not just a formula dumping thing. However, it does give you the coordinates of these points. So if you need the coordinates, then this is a good process to go through to get. Okay. Right, that finishes all the content of the video. I did say it was going to be a long one. We're 43 minutes in. Let me just very quickly summarise all of this. Welcome, if you jump to the summary. We're looking at all we've done in this video. So the formula to get from point to point, 2 points in three-dimensional space, is just Pythagoras, which looks like this. You're not given that formula, you need to learn it, but that's so easy, you should know that already, so not a problem. The next one is point to line. So we've got general point, general line. The distance between those is given by this formula, which was derived earlier. This is also not given in the MEI spec, so you need to learn that formula. Distance between point to plane, got general point, general plane. This is the formula for the distance, minimum distance between those two objects. This one is given in the formula book, so you don't have to learn it. Distance between two skew lines, line 1 and line 2. That is this formula. That is also given. And one thing I didn't touch on is what happens if the lines are parallel. Okay, this is only true if the lines are not parallel. If the lines are parallel, that is, if D1 is some multiple of D2, then we can't use this formula because you end up with a 0 divided by 0 situation. It's a degenerate case. What you do instead is, rather than calculating the shortest distance between the two lines, we are instead going to take 1 point on one of the lines and find the shortest distance from that point to the other line. Okay, if you imagine that you've got, colours I used, this is orange. If you imagine I've got two parallel lines like that, then the shortest distance between them is going to be equal to choosing one of the points on one of the lines and finding the shortest distance between that and the other line. That is the shortest distance between those two. Okay, so that's exactly what we do. So instead of using this formula, which is the distance between two skew lines, we use this formula, which is the distance between a point on one line and the other line. Okay, again, that's not given because that is this case. Okay, so if they're parallel lines, you've got to use this formula to calculate the distance. If they're skew lines, you calculate this one. Okay, right, and I think that that finishes everything I wanted to do. So if you stuck it out for the full 45 minutes, massive well done to you. It was a long one, but that was quite a journey. In the next video, we're going to be using these formulae in some questions, just so you can see them in action. Because we've not done any of that in this video. All I've done is derive them, explain them, and lay them out in front of you. Okay, but now we're going to use them in the next video, maybe two. We'll see how we get on. Thanks so much for watching. Please add comments if you are unsure of something. And yeah, enjoy the rest of your day.